Imagine a team of AI agents working together, each one smarter than the last, collaborating to solve a complex visual reasoning task. One agent sees a plate of food. The next interprets the image through the first agent's description. The third builds on that. And by the fifth turn, the final agent confidently declares, "This meal is marinated pork strips, and it's extremely high in salt." But here's the catch, there's no pork on the plate at all. This isn't a bug. It's a failure mode that's quietly spreading across multi-agent AI systems, multi-agent visual hallucination snowballing. Today, we dive deep into a groundbreaking paper from the National University of Singapore, Tencent Youtu Lab, and Zhejiang University that uncovers the root cause of this phenomenon, and introduces a simple, plug-and-play solution called ViF, which dramatically reduces hallucinations across 8 benchmarks and 10 base models. Let's break it down step by step. The problem, when AI agents trust each other too much. Multi-agent systems powered by visual language models are becoming the backbone of complex AI tasks, collaborative reasoning, multi-turn instruction following, and multi-modal understanding. But here's the twist. The more agents you add, the more likely you are to go off the rails. Why? Because each agent relies on the textual output of the previous one to understand the image. That's the core of the problem. When Agent 1 misinterprets an image, say, mistaking a banana for a sausage, it doesn't just make a mistake. It relays that error in text. Agent 2 then uses that flawed description as a foundation. Agent 3 trusts it. And so on. The error doesn't just persist, it snowballs. This isn't just a single-agent hallucination. It's propagated hallucination, where the textual flow becomes the dominant signal, drowning out the original visual evidence. And the worst part? It's not obvious. The final output can sound perfectly coherent, plausible, even while being completely wrong. So what's really happening inside the model? The researchers conducted a detailed turn, layer, and token-wise attention analysis, a deep diagnostic of how the model allocates attention across its internal layers. They found a consistent pattern. As agent turns increase, the model pays less and less attention to the visual tokens, the raw image features encoded by the vision transformer. In the first agent turn, the model clearly focuses on the image. There's a sharp, unimodal peak in attention, meaning a few key visual tokens dominate the processing. But by the 20th turn, that peak has disappeared. Attention becomes flat. No clear visual signal. Meanwhile, attention to instruction tokens, the text from the prior agent, grows steadily. The model is increasingly relying on what was said, not what was seen. This is the hallucination snowballing mechanism in action. Visual fidelity degrades over time, and the model starts treating textual descriptions as authoritative, even when they're wrong. Here's where things get fascinating. Not every visual token is the same. The researchers discovered a small but critical subset, vision tokens with a unimodal attention peak in middle layers. These tokens are special. They're semantically coherent, highly relevant, and carry the most visual evidence. When you remove them, visual understanding drops dramatically, especially in middle layers where vision and language fuse. But here's the kicker. The proportion of these unimodal tokens shrinks over agent turns, from 1.22% in the first turn to just 0.1% by the 20th. They're being drowned out by noise. Forgotten. Lost in the textual flood. So the real problem isn't just reliance on text. It's the systematic erosion of visual signal integrity across turns. Enter ViF visual flow. Instead of letting agents pass only text, ViF introduces a dedicated visual relay channel, a lightweight, plug-and-play module that preserves the most important visual evidence. Here's how it works. First, select the right tokens. ViF identifies the unimodal vision tokens from the previous agent's output, those that best preserve visual truth. Second, contextualize the visual relay. These tokens aren't just passed raw. They're contextualized with the current instruction, using a small transformer block. This ensures they stay relevant to the current task. Third, reinforce visual attention. A novel attention reallocation mechanism amplifies the visual signal. In middle and deep layers, it boosts attention to the selected visual tokens and redistributes attention from inactive or overused tokens, like instruction tokens that are now dominating the conversation. Fourth, insert into the pipeline. The visual relay tokens are inserted between the original vision tokens and the instruction tokens in the next agent's input. So the next agent sees both the text and the preserved visual evidence. Think of it like this. Instead of passing a summary, you're passing a visual snapshot, a curated high-fidelity signal that resists degradation. The results are striking. On 8 benchmarks, including comprehensive evaluations like MME, MMBench, and MemVR, and hallucination-focused ones like Pope, Chair, and Hall Bench, ViF delivers consistent improvements, an average of 2.4% to 4.4% across all models. On the most challenging benchmarks, where hallucinations are rampant, ViF improves performance by over 4%. Even more impressively, on larger models like L-Lavani XT34B and Qwen-VL 32B, the gains are even bigger, up to 4%, because these models have more potential and ViF unlocks it. And when it comes to hallucination snowballing itself, ViF reduces the hallucination score by up to 40%, cutting the snowballing effect almost in half. You might ask, why not just use existing hallucination mitigation techniques? Methods like MemVR, TAME, Farsight, and Vista focus on single-agent hallucinations, fixing errors in one model. But they don't address the core issue, textual flow as the primary relay. When you apply them in a multi-agent system, they often make things worse. Why? Because they tweak the decoding process or attention, but they still rely on text to pass visual information. So the model still over-relies on flawed descriptions. The hallucination propagates, even if it's slightly less severe. ViF, in contrast, breaks the chain. It doesn't just reduce hallucinations, it replaces the flawed relay mechanism with a visual one. This isn't just academic. It's critical for real-world applications. Imagine a medical AI system, where doctors use a multi-agent VLM to analyze X-rays. One agent misreads a tumor. The next builds on that. By the end, the final diagnosis is wrong, but the system sounds confident. Or a self-driving car, using multi-agent reasoning to interpret traffic scenes. A misidentified pedestrian. That's not just a glitch, it's a safety hazard. ViF offers a practical, efficient fix, a lightweight module that can be added to any VLM-based MAS, no retraining, no model overhaul. It's plug and play. It works with LLaVIA, Qwen, and even larger models like intern-VL and mini-CPM. And it's robust. Even when you reduce the number of visual relay tokens by 50%, ViF still outperforms the baseline. This paper doesn't just fix a problem, it redefines how we think about information flow in multi-agent systems. The lesson: text is not the only or even the best way to pass visual knowledge. By identifying the right visual tokens and creating a dedicated visual relay, ViF restores visual fidelity across turns. It prevents the snowballing effect not by suppressing hallucinations, but by preserving truth. This is a turning point. For the first time, we're not just fixing hallucinations in AI agents. We're designing systems that inherently resist them. So the next time you see a multi-agent AI working together, remember, the most powerful signal isn't the one that's said. It's the one that's seen. And now, thanks to ViF, that signal can finally be passed on without distortion. Want to try it yourself? The code is available at github.com/yudeep/ViF. And if you found this breakdown helpful, hit like, subscribe, and let me know in the comments. What's the most surprising thing you learned about AI collaboration today? Until next time, stay curious.